2021. The first lecture in today is the special lecture by Professor Mazin, and this will be on superconducting single photon detectors and its various applications. So I request Souvik Chatterjee to introduce the speaker and chair this session.
Thank you, Pratap. Good morning, everyone, for joining us in the second day of QMAT. Today, we have a very special lecture from Professor Benjamin Mazin, who is currently the Worcester Chair in Experimental Physics at University of California at Santa Barbara. He received his PhD at Caltech, graduating with a doctorate in astrophysics in 2004. After that, he went to JPL in March 2005. And after that, he joined the faculty at UC Santa Barbara in 2008, and he's been there since then. He's a world-renowned expert on microwave kinetic inductance detectors and astronomical instrumentation for time and energy result studies. His current research focus is building and using these MKID-based instruments for detecting and characterizing nearby exoplanets. He was awarded the Presidential Early Career Award for Scientists and Engineers in 2010. So with that, I'll hand it over to Professor Benjamin Mazin for his talk. Before that, just a quick comment. We generally don't take questions during the talk. If you have questions, please feel free to write it in the chat box. And after the talk, we will have a Q&A session for about 10 minutes. So with that, over to you, Professor Mazin.
All right, thank you, Dr. Chatterjee. I will take it from here. So thank you for coming this lovely evening in Santa Barbara, morning for you guys. I'm going to talk to you today about microwave kinetic inductance detectors, which are superconducting detectors that tell you the energy and arrival time of every photon in the optical and near infrared wavelength range that hits your detector without false counts, without read noise or dark current or some of the things you can have happen in a semiconductor detector. And I'm going to tell you about the applications that we use them for, exoplanet detection, and a little bit about dark matter and biological imaging, some of the other applications that we think are promising for these detectors. So this is work that's been done here at UCSB with my group, shown pre-pandemic down here on the right. There have been a couple faces that have changed since we all were, in one place without masks. But this is a good cross section, and this is work that takes a lot of people to do. We do everything from developing the materials for novel low temperature superconductors to doing lithography and device design and testing, all the way to building instruments and the readouts for the detectors, bringing them to the telescope, taking data, publishing science papers. And so there's a kind of a vertically integrated version of astronomy that we're doing here, or physics. It really crosses the boundaries between condensed matter physics and astronomy. And so it takes a bunch of people to do it. And we have collaborators too around the world, like at Subaru, Caltech, JPL, and other places listed here. All right, so as you probably know, astronomers and physicists tend to use CCD or CMOS detectors in the optical to near infrared range to convert photons into electrical signals. So these are semiconductor detectors. A photon hits the semiconductor, knocks an electron into some conduction band. It's shuffled around with electric fields until it eventually gets read out through some semiconductor amplifier, and that photon is then translated into an electrical signal that we then can get into a computer. These devices are amazing. You can buy. There have been billions, if not trillions, of dollars spent on semiconductor detectors, and there was a Nobel Prize awarded for the CCD. On the bottom left, you see a Mercad telarray from Teledyne, and on the right, you see the dark energy camera. It was about a 500 megapixel CCD mosaic. These detectors have enormous dynamic range. They are extremely uniform. They have very good pixel to pixel variations. They're very calibratable. They're really amazing pieces of modern technology. And there is a bit of hubris in thinking that my lab with me and a couple grad students can beat the performance of these detectors. And to be clear, we can only beat the performance of these detectors because we're working, we're willing to do things that commercial vendors are not. We don't have to sell these for money. So we're allowed to optimize to the limits of what physics and what our budget allows. And that's kind of where that's our sweet spot, doing things that a commercial vendor wouldn't do, and optimizing, especially for the application we're doing. And for astronomy, that often means very low light regimes, or we want fast photon counting, and we want wide bandwidths. So that's what I'm going to tell you about today. So this is just the operation of a CCD, a charge coupled device. Basically, what happens is you have a photon hit a piece of silicon, it creates an electron. There are wells made with electric fields that confine that electron and then eventually shuffle it around the chip until it eventually gets into the serial register and gets read out by an amplifier at the end. These the primary drawbacks of this kind of detector are first that the amplifier at the end of the chain here adds read noise. So even in the best CCDs, you usually get something like 2 electrons of read noise when you read out the number of electrons in one of your pixels. There can also be thermal effects. So you can have you can generate charge in the semiconductor from thermal effects, which we call dark current, which looks like just extra charge showing up in your array. And also you can have radioactive decays or muons we call cosmic rays that leave trails of charge through the detector, which show up as artifacts in your image that you have to get rid of. So to do better, we need to change our technology. So what we do is we go from semiconductors. So silicon has a band gap of 1.1 electron volt. All right. So that's where we start with. A superconductor, though, has an analogous gap. That's the energy it takes to break a Cooper pair in the condensate. That is about 0.1 millielectron volts for the materials that we use. That means that your energy gap, the equivalent energy gap, it's not exactly the same, but it's sort of equivalent, is about 5 or 10,000 times lower. So when a photon hits our superconductor, it doesn't free 1 electron. Well, it does in the beginning, but then that energy cascades down. And so when a photon hits a semiconductor, you get 1 electron. When a photon hits a superconducting detector, you get 5 or 10,000 freed electrons, which are our signal. And by counting the number of electrons that are freed from a photon, we can actually tell you the energy of the photon that hit the superconductor. That's the true power of these detectors. The downside is that they're superconductors, which means they have to be very cold. So we operate our devices below 100 millikelvin typically. They don't support electric fields. They're perfect conductors. So we can't play these games of shuffling charge around that they do in semiconductor devices. And finally, the excitations are short-lived. In the superconductors we use, when a photon hits, it breaks up a Cooper pair and you have these 2 electrons floating around. But then they find a buddy and they want to pair back up and to form a Cooper pair. And that time scale we call the quasi-particle recombination time is roughly 25 to 50 microseconds. Maybe in some of the some of the materials it might be as long as 400, but we're talking about microseconds scales. So whatever you're going to do to read out that disturbance in your superconductor, you have to do it on a very short time scale. So the way we choose to do it is we use something called the kinetic inductance effect. So the kinetic inductance effect is a property of all metals. When you start a current moving, you store energy in that current, in the kinetic energy of the moving charge carriers. In a normal metal, there's so much scattering that information is quickly lost, and the kinetic inductance tends to be a very small factor compared to the normal geometric inductance in a circuit. In a superconductor, though, you can store a lot of energy. It turns out you can tweak your parameters and store quite a bit of energy in the motion of these Cooper pairs. So you can start a current flowing, but if you want to have an AC field and get that current moving back in the other direction, you have to remove the energy you put in. And so that means from the time you flip your electric field and try to get the electrons moving the other way, there's a delay in that response, and that's equivalent to a lag, which is equivalent to an extra inductance. And in the superconductors we use, the kinetic inductance typically dominates the geometric inductance and is by far the largest inductance in our circuits. So this is what an M-KID looks like. You have this is a circuit schematic, and this is drawn as a microwave circuit. So if you're used to looking at DC circuits, this would usually be a ground in your circuit right down here. But the way it works is it's just a little LC oscillator. It's the simple harmonic oscillator that you've seen a million times in physics. So you have your inductor, you have your capacitor. Some people call this a tank circuit. And then you have this small coupling capacitor that couples you to a microwave feed line that brings the signal past the device. So when you're on resonance, you have energy sloshing back and forth between the inductor and the capacitor here, at the resonant frequency 1/√square root of LC. The trick is that we make this inductor out of a superconductor. So when a photon comes in, it breaks the Cooper pairs, and that changes the surface impedance of the film. So what actually happens is the inductance goes up slightly and the resistance goes up slightly when a photon hits it. And then this, so the way we read this out is we send a microwave probe signal, just a sine wave, at the near the resonant frequency F0 of this circuit. And so this forms what you probably refer to as a notch filter, right? So what this means is that when you're on resonance, most of the power is actually reflected back from this circuit. And when you're off resonance, the microwave signal just passes by unaltered. So we actually we do look at both the phase and the amplitude, but the biggest signal is in the phase direction. So we can send a microwave signal past this little LC resonator, and then we watch right here at the end of the circuit to see what happens to the phase of the signal that we sent in as a photon gets absorbed. And so if we look at the phase, you see this plot on the right where you have some noise, which has caused this. In this case, this is from our amplifiers that we're using in the system. In this case, it's actually a quantum limited parametric amplifier called a TUPA, or traveling wave parametric amplifier. And then the photon comes in, you see a quick change in the phase. That's on the order of a couple microseconds, and then the pulse decays back down to the baseline with a time scale of about 50 microseconds in this case. And so this is our photon event. This is a single photon hitting a single resonator, and this work was done by my grad student Nick Zobrist. So there's a lot of information encoded in this pulse. The first thing is that you can see that the arrival time is very clear when you see this jump. So you can tell when this photon came to maybe a couple microseconds, 2 microseconds. You can also tell the energy of the pulse, or the wavelength of the photon that hit, by the height of the pulse. So a tall pulse, or in this case, a large negative pulse, means you had a blue photon. If you had a smaller pulse, the one we'll say to here, that might tell you that you had a red photon. So we can calibrate this by putting in lasers of known wavelengths and doing this calibration. And that's what I'm showing you down here. Now, this is recent results that we just submitted for publication, showing the energy spectrum of a hafnium-indium bilayer device. I'll talk about that in a little bit, but we're using a quantum limited parametric amplifier, and we're using essentially a phonon engineering scheme to reduce one of the primary noise sources in our devices, which I'll talk about soon, and to get these world record results for a device suitable for integration into a large array. You can see we're getting a spectral resolution of about 33. That's E over delta E. So the energy over the full width half max of this Gaussian at the energy of our photons. So this is great, and there's a ton of science that we can do with arrays with these properties. So I've talked about one device. Let me show you how we make them into larger arrays. So what we do is, and we haven't talked about the actual detector design. So let's start there. So I showed you down at the bottom left, this is the same circuit schematic of the M-KID. So the biggest thing that draws your eye, circled in this blue box, is an interdigitated capacitor. So this is just a capacitor formed with interdigitated fingers. We can control the capacitance by pulling back the fingers of the capacitor to limit the amount of overlap, which lowers the capacitance. So that's how we tune the resonant frequency of each detector, by changing the capacitance. The capacitor is big because one of our noise sources, two-level system noise, is due to two-level systems on the surfaces and especially the interface between the metal and the dielectric of the substrate. Those can cause RF noise, and so we maximize the size of the capacitor because it lowers that noise source. The next important part of the circuit is the meandered inductor. You can see that up here. This is our photosensitive region. This is just the L. It's got this double meander to reduce crosstalk between nearby circuits. So a photon has to hit in this red box for us to sense it. And by the way, to give you a sense of scale here, this pixel is about 150 microns across. So the pitch from one pixel to the next is 150 microns. The gaps in here are 0.3 microns. So this is made with a deep UV lithography process. When so we have to hit here. So our quantum efficiency would be terrible if the array just looked like this, because the inductor covers such a small fraction of the total area of the pixel. What we do, though, is we take a trick from the CMOS detector people, and we use a square microlens array that's held in front of our array. That focuses the light that's coming in down to a spot at the center of the inductor here and recovers an effective fill factor of something like 72%. Sorry, about 92%. You can also see when you zoom out to the larger array, we have a design that has a coplanar waveguide feed line. This is what brings the microwave signal into the array. And this snakes back and forth and couples to every pixel, allowing us to make large arrays. And I'll talk about that right now. This is what makes MKIDs such an attractive detector for especially this wavelength range. They have this built-in frequency domain multiplexing. So before I showed you that the transmission off resonance is nearly perfect, because the transmission is nearly perfect off resonance, if you have another resonator at a different frequency sitting next to that original resonator, it won't interact with it. They basically ignore each other. And so what we can do is we can stack these resonators at different frequencies on a feed line. What we do now is we use the 4 to 8 gigahertz band. We start at 4 gigahertz. We put our next resonator 2 megahertz above it, so 4.002. The next one, 4.004. And by doing that, we can put 2,000 resonators and therefore 2,000 pixels on a single microwave feed line. That is, that's what lets us read out these big arrays of MKIDs. And that's something that's very difficult to do with other superconducting detector technologies. All right, so I will do a little condensed matter physics because this is a quantum group. But I'm going to talk more about applications. So get your quantum questions in now. All right. So what we have here is on the top left is a diagram showing something called athermal phonon loss. So what happens when a photon hits our detector is it quickly it hits an electron, and that single electron takes most of the energy. Then there's a cascade where the phonons and where that electron interacts with the rest of the superconductor, and the energy gets shared between broken Cooper pairs called quasiparticles and the phonon system. But sometimes you can lose a high energy phonon out of the detector and into the substrate before the phonon fireball completes and before you essentially reach local thermal equilibrium. So, and this limits our spectral resolution. Both us and a group in the Netherlands at ESRAN has seen that this athermal phonon loss limits our detectors on a solid substrate to something like a spectral resolution of 10 or so. You can see, actually, I don't have the plot of what it's like, but it's about 10 at 1 micron is about the limit you can get because of this loss. So what we've recently figured out is that we can put a thin layer of indium underneath the hafnium superconductor. Because indium has a much lower Debye temperature, it can't support all the phonon modes, especially the high energy phonon modes that you get during that initial down conversion. And so the phonons essentially get trapped in the detector and can't get out until they've down converted to a lower energy. So this is shown on the right panel. This is this is how we use this layer to get something like R of 33 at 400 nanometers. We have a full noise model now, and we're pretty sure that we're still limited by this athermal phonon escape. Even the barrier isn't perfect, and so we're working on more advanced methods to try to keep all the phonons in the detector until they've down converted below the gap energy of the superconductor. The bottom left here shows the Fano limit. This is the fundamental limit to MKID resolution. So if you get rid of athermal phonon escape and amplifier noise and all these other things, this is the fundamental noise that's created by the quasi-particle down conversion process, where the phonon turns into a bunch of quasi-particles. And this sets the ultimate limit based on the operating temperature of the detector. So for 400 nanometers and an operating temperature of about 40 millikelvin, we think that the Fano limit tells us we should be able to get to spectral resolution R of over 150, and so that's where we're aiming in the coming years. All right. So here's one of our arrays. This is a 10,000 pixel MKID array for the darkness instrument. We brought this to Palomar and did a bunch of experiments with it. We've actually built 3 instruments based on this 10 to 20 kilopixel MKID technology. Darkness at Palomar, the MEC camera for Subaru, which I'll talk about a lot more, which is currently on Mauna Kea taking data. We've also built a balloon-borne version, although the flight has been delayed indefinitely due to COVID. Okay, here's the array for MEC. This is a 20,000 pixel platinum silicide. That's the superconductor we use for the MKIDs array for the Skexeo MEC instrument. It's 140 by 146 pixels with 150 micron pixel pitch. This is a 22 by 22 millimeter imaging area. So this microwave package essentially fits in your hand. There's 10 microwave feed lines using G3PO connectors that bring the signals down to the array, and this is the spectral resolution that we get from this device. This is published in a 2017 Optics Express paper by my former graduate student Paul Shippert. A lot of the work we do, making the arrays is not enough. You actually have to read them out to do anything useful with them. So a lot of that is done with these digital MKID readouts. They're based on a technology called software-defined radio, which leverages really massive investment from communications firms in ADCs and FPGAs for fast signal processing. I won't go into this too much, but the general idea is that we create a comb of frequencies, one tone to hit each resonator. We send it through the device out of the fridge after amplification, and then we digitize the entire wideband, 4 to 8 gigahertz signal. Then we use room temperature electronics to figure out what photon hit what detector and what impact it had. So there's a ton of signal processing, and we've got a lot of work put into this and have a working system. So here's our Gen 2 readout that we developed in collaboration with Fermilab. It's based on the Casper Roach 2 board, which uses a Vertex 6 FPGA. It has dual 2 gigasample per second 12-bit ADCs and DACs. It reads out 1,024 pixels in 2 gigahertz in one of these boards. There's another identical board on the other side, and so each one of these cartridges reads out a full feed line. So we have 10 of these cartridges to read out a 20,000 pixel array. It uses roughly 3 kilowatts of power. Costs something like $5 to $10 per pixel, excluding the HEMPs and which we are in the fridge and I didn't count, and the FPGAs, which we got donated. So this is a powerful readout, but is a tremendous amount of signal processing. The front end data rate coming out of the ADCs in this system is about a terabit per second. And so we can't store a terabit per second of data. And so we end up doing a lot of work to compress the information down and into the minimum amount we can safely store. It turns out we actually every photon gets recorded within about 50 microseconds as a 64-bit word on our server. And that 64 bits contains the pixel identifier, XY position, the arrival time, and the energy of the photon, essentially. We're currently almost done developing a 3rd generation readout based on the Xilinx RFSoC, which integrates an FPGA with the analog to digital converters and the digital to analog converters all in a single package, which means that a lot of the difficulties of communicating between the ADC and DAC and the FPGA are taken out of your hands. This is incredibly good for power consumption, but it also improves the capability significantly. So our readout based on this work by my grad student, Jenny Smith, is we basically have a functional readout, and we're going to be hopefully publishing something on this early next year. Once you get the data, though, you're not done yet, right? You just have a giant list of photons on your computer. It doesn't look anything like an image. And so in order to turn that list into something useful, you have to do a lot of data processing. And this is big data. We take several, on a night on the mech instrument at Subaru, in 8 hours or 10 hours, we might take 1 or 2 terabytes of data. And we have to process that data. So we have an MKID pipeline. It's available at GitHub/Mazin Lab. We're about to submit a pipeline paper on it, but there's a whole lot of work in turning this data into some kind of data product that an astronomer can process. So maybe we want FITS files, maybe we want a series of images, maybe we want a series of image cubes. All of these things are possible by using the data pipeline and getting the data outputs you want. We've spent a lot of time building this up for science purposes. Okay, so here's where I'll change directions and start talking about the applications of these systems. The one that really is most exciting to me is exoplanets. So there are over 4,000 confirmed exoplanets, mostly from 2 techniques. There's the radial velocity technique that uses the Doppler shift of the star to detect the wobble induced by planets. And then there's the transit technique, which looks for dips in the light output of a star when a planet eclipses it. There's even one of these, but what we've learned in the 25 years since planets were first discovered outside our solar system is that they're very common. There's even one around our nearest star, Proxima Centauri b, and it might even be in the habitable zone of Proxima Centauri b. What we really want to do now is not just find these planets, but we want to be able to characterize them. Especially, we want to be able to look at their atmospheres and see if they're in chemical equilibrium, like say Venus, or if they have been altered by some kind of process like life, like Earth. And so there's a lot of work going towards this. This is the highest priority of the U.S. decadal survey that was just released, Pathways to Discovery, that will be set the course of astronomy, hopefully for the next decade or more. But they chose the direct imaging of these exoplanets as the highest priority, both from the ground and from space. And so I'm going to tell you about how we're doing it from the ground. Before I go, just a little exoplanet information for those who haven't been paying too close attention. This is kind of a summary of what we know about exoplanets. On the bottom axis is the orbital period of the planet. So 1 year would be, here at 365 days. The y-axis is the mass of the planet in Jupiter masses. So Earth is like 1/300th of a Jupiter mass. So Earth would be sort of down here, somewhere in this region right here. You'll see that there are not many planets in that region of parameter space. It's not because those planets don't exist. It's because they're very hard to detect. So there's selection biases in these techniques. Transits, which were mostly done with the Kepler satellite, can find small planets, but they like to find planets that are very close to the star so that they transit frequently. So that's the green points here. Radial velocity, which looks at the tugging of the planet on the star, that likes, stars are pretty massive, so you need a pretty good sized planet to tug on them. So the radial velocity likes to find massive planets, and those are shown in red here. So what do we have to do to push down into this region here? That's what we'll talk about for the rest of this, for a lot of the rest of the talk. Okay, so what we want to do is use a technique we call direct imaging. Direct imaging is a different method besides transit and radial velocity method for looking for planets. And it's conceptually the simplest. We're basically going to take a picture of a star system. Ideally, we point our giant space telescope at a star, we take a picture, and we see a bunch of little bright lights around it, and we're done. Unfortunately, it's a lot harder than that because first off, the star is vastly brighter than the planets, and so we need to do a lot of work to get around the brightness difference between the star and the planet. The other problem is we're not in space. We're on the ground, and there's the atmosphere in the way. The atmosphere causes stars to twinkle. Basically, there's turbulence in the upper atmosphere. There are high-level winds, and as the light comes through the atmosphere, those temperature fluctuations cause dielectric constant fluctuations, and so the light gets bent as it goes through the atmosphere. This blurs the star out and erases all information about, or makes it much harder to recover the information about what the clean, unaberrated wavefront looked like above the atmosphere. So the first thing we need to do is fix the blurring that the atmosphere puts in. We do that with a technique called adaptive optics. So in adaptive optics, we take the light from the telescope, then we bounce it off a rubber mirror. So this is a mirror that has a thin face sheet, and behind the mirror are a bunch of pistons that can move back and forth. So what we do is then we take the light that's bounced off this deformable mirror, we look at it, and we know that it should be a perfect point source. And so we then do a bunch of linear algebra to figure out what kind of problems could have been introduced in the wavefront that would give you what you see. And then we try to fix that with this rubber mirror by changing these pistons to restore as close to a diffraction limited image as we can get. Because the atmosphere is constantly changing, we have to do this fast. So we have to do this something like 2,000 times a second. And even then, it is a very challenging process. This is not something I personally work on, but my collaborators at SkexAO are experts in the process of correcting wavefronts with adaptive optics. So this is step one of detecting taking a picture of a solar system. And this is what you can get when you actually do it. So this is HR 8799. This is a planetary system that was discovered with the Keck telescopes in around 2008 using this adaptive optics technique. And then they use adaptive optics, and then they use a PSF subtraction technique called angular differential imaging that allows you to subtract out the PSF of the star using the field rotation of the image. So each one of these dots of light is a planet. They're over 10 Jupiter mass. They're somewhere between 5 and 10 Jupiter masses. This is the A star, which means it's more massive than the sun, and it's quite young. So these planets are still glowing in the heat of their formation. So this is what we want to do. This is like the holy grail of planet finding. And this was an awful red herring for the last decade, because it turns out that this system's a bit of a unicorn. We haven't found very many other systems that have this kind of planetary system orbiting them. It was very rare, and it led us down it might have led us down some blind paths. But it is an example of that the technique is working. The problem is that these planets are maybe a part in 10 to the 5 of the brightness of the star in the infrared wavelengths we're looking at here. Planet like the Earth around the sun is closer to 10 to the minus 10 brightness. So significantly fainter. And so we have to do better than this if we want to start pushing down to planets that might have life on them. So the next thing we have to add to our system is called coronography. So this is basically putting a opaque spot over the bright star on axis and then trying to pass light off axis. This is my example of doing it with my iPhone camera here at UCSB. And you can see my thumb is blocking out the sun, and I'm able to image, probably closer to the sun than I would have been able to if my finger wasn't there. There's a ton of technology and experience involved in coronography. This is also not what I do for a living, so I'm going to skip it. But I will say that this coronography is really important. It is not what limits our performance of our currently. The wavefront control from the adaptive optics that I talked about is more of a limit than the coronography. Okay, so you did step 1, AO, you did step 2, coronography. Step 3 is actually detecting the planet around the other stars. This is the science instrument that takes the light that's gone through these systems and then lets you find the planet. This is where the MKIDs come in. So our MKIDs are what we call integral field spectrographs. They give you the spectra of every pixel in your array. The MKIDs have you can make such a thing, an integral field spectrograph, with conventional detectors. It's usually done with a lens lit array that breaks the field up into a bunch of little points, and then you disperse them with like a grating or a prism, and you make lots of little spectra, one for each pixel. So the top right is an example of a conventional Mercad tel detector that's been turned into an IFU. And what you're seeing here is a movie being played. Every frame in this movie is a different wavelength, starting at about J band, about 1.1 microns, going out to K band at about 2.4 microns. And you can see some interesting things. There's all these features, and as the wavelength changes, you see these features grow. That's because these are speckles, which are caused by interference. They're the background that we want to get rid of, but they're wavelength dependent. So by having this integral field spectrograph, you can see that these speckles move out with wavelength, where this brown dwarf right here does not. And so this is a way that we do something called spectral differential imaging. We use the wavelength change to try to distinguish between a planet and the speckles. You see, if I pause the movie, there's lots of things in the field like this and this and this that look sort of like what we see for this brown dwarf. But as soon as we play the movie, they all start moving, and it becomes easy for your eye to pick it out. So this can be done with conventional detectors. The bottom right is our version of this with an MKID detector. We were getting a very narrow slice of wavelength, so there's not as much speckle motion here. But the MKIDs have another advantage that these semiconductor detectors don't, which is that they're very, very fast and they have no read noise. And so that allows us to use temporal statistics to determine if a photon came from the planet or whether it came from the star. So to do this, we use something called the MEC camera. MEC is the 20,000 pixel MKID exoplanet camera for a Subaru SKEX-AO. Here's a picture of the inside of MEC. You see we have a magnetic shield down here that contains our MKID array. We have these niobium titanium flax cables that we developed in my lab and published that bring our signals down from 4 Kelvin to about 100 millikelvin. And we have a block of hemped amplifiers and some more of these compact cables that we built to make this work. This picture shows us delivering the instrument at the summit of Mauna Kea. You can see the Keck telescopes in the background and a very cold driver who drove these up from Hilo to the very cold summit. So here's a picture of my grad student Alex next to the MEC instrument. MEC is housed in an adiabatic demagnetization refrigerator, which is a very compact system that allows us to get to these low temperatures. So this compact system is quite convenient to bring to telescope and mount to an instrument like SKEX-AO. And here you can see the instruments. There's AO-1E88, which is a first stage adaptive optics system, SKEX-AO, which is a second stage adaptive optics system, and coronagraph, and the MEC and CARIS instruments, which are science instruments that use the light from Subaru. Okay, so here's a nice example that I like to show. The bottom left shows the data that's coming from the telescope integrated into 1/10 of a second frame. So every frame here is a 1/10 of a second, and the right is the integrated image. So this integrated image is what a conventional detector gets. But on the MKID, on these shorter timescales, you can just see that the AO system, you can see these dancing speckles going all around and blowing up and coming in and out. The AO system is not stable. And the advantage is that the MKIDs have the time resolution to see this and to try to fix it. And that's what my grad student Noah is currently working on. We use a technique called stochastic speckle discrimination. What this means is that the light that's in a speckle, which are like we artificially induce speckles B and C by putting a pattern on the deformable mirror. So A is an actual companion, and B and C are speckles that we induce, that we create with the deformable mirror. These speckles are a interference pattern, right? So you have their starlight interfering with itself. And just like when you shoot a laser beam at a wall, when you have an interference pattern, it has different arrival time statistics than you would get from a normal source, which would have Poisson or shot noise statistics. So, in this total intensity image, you can't tell the difference between the real companion and these speckles that are in our field of view. However, when you look at the arrival time histogram, you can see a big difference. So what we do is in this case, we bin the data into 20 millisecond bins, and we count how many photons arrive in every pixel in that 20 millisecond bin. And then we make a histogram of it and fit that histogram with either a Poisson distribution or with a different statistic called the modified Riccian, which is what you expect from this interference pattern. And what you can see is that this top here is location A, which has this nice Poisson distribution. The bottom intensity speckle B has this much broader distribution. You see, it's much more likely to have very few counts or very high counts than you'd expect from a Poisson source. And so by looking at the statistic, you can tell the difference between the two. So this is an example of us doing that with MEC data. This is data published by my grad student, Sarah, on the star HIP 109427. So this is, on the left, is the total intensity image we got by just integrating about 15 minutes of data from this star. And you can see there's a spot here, but if I hadn't circled it, your eye probably wouldn't have picked it out. This spot's also pretty bright. There's something here. Maybe you could see something here. These little things in this little cross is a calibration artifact that we intentionally induce. So that's nothing important. Okay, but then when we run this stochastic speckle discrimination code, which looks at the arrival time statistics of every photon, suddenly the companion pops way out, and you can see it at a much higher signal noise. This is really exciting because this technique, most of the techniques you use to reject this speckle background fail as you get close to the center of this image because they rely on field rotation or the motion of speckles. This technique does not, and so it inside close to the star where you expect most of the speckles to be. This is a world. This technique is extremely powerful and probably better than the other techniques I've talked about for finding companions. We can do other things too. This is an example of some data we took on the AB Auriga system. On the right here, this is an image from Subaru taken in polarized this was taken with the sphere instrument on VLT, showing this debris disk around this young star AB Auriga. The left panel is the MKIT SSD image, which was taken in total intensity, not polarized intensity. So this would not have been possible without the SSD technique, and we recover a lot of the features that are shown on this plot. So we're currently preparing this for publication. We think this is a really interesting technique for finding disks going forward without polarization. All right, so what we really want to do with MEC is we want to see a planet in reflected light. All the planets that have been detected so far with direct imaging, and let's be clear, there haven't been that many, are more massive than Jupiter, very young, and outside 5 AU or something. So they're pretty far from their parent star. What we want to do is push our contrast levels down with these fast focal plane techniques that MEC allows, and push closer into the star and to fainter contrast and uncover some stars. Our main target here is a GJ876b. This is kind of a really interesting planet. So this GJ876b is a M dwarf, so it's a small star, much less massive than the sun, and it's got a large gas giant Jupiter-like planet orbiting around in the habitable zone, actually. So orbiting, in a fairly short orbit. And this looks like, this has been discovered with the radial velocity technique, but we don't know anything about its atmosphere because radial velocity doesn't tell you anything about it. this is our test case that we think we can get to with MEC with enough tuning. However, we are not going to be able to get much better than this. You know, the best we can do with this technique is going to be essentially Jupiter mass planets, you know, at 1 AU, you know, gas giants. We're not going to get to the planets that can that we're really interested in for finding life. And so what we need to do to find life is we need a bigger telescope. The figure of merit that matters for these kind of observations is it's something like telescope diameter to the 4th power. So going from an 8-meter telescope like Subaru to a 30-meter telescope like the TMT, the 30-meter telescope, gives you something like a factor of 200 in performance improvements. And so you go from just barely seeing the biggest, youngest stars on the planets in the stellar neighborhood to actually being able to hopefully see the rocky planets in the habitable zones of nearby M dwarfs. We need to get to something like 10 to the -8 contrast ratios for these M dwarfs, but there are 275 of these M dwarfs within 10 parsecs. We know they have rocky planets like the TRAPPIST-1 system. So this is our goal. All of our work now is sort of a lead up to this, to being able to do this with these 30-meter telescopes. India is a partner of the 30-meter telescope, and we're always looking for scientists who are interested in collaborating on this project in our partner countries. So feel free to contact me if you have any interest in TMT or exoplanet detection and want to talk. Okay, so now I'm going to talk about some other applications that we're doing with MKIDs in the last 10 minutes or so here. So one of the things that we're really excited about is using the MKIDs not just for an integral field spectrograph where you just take the MKID array and stick it in the field of view of a telescope and call it done, but use MKIDs in more complicated instruments to enable new capabilities. And one of these is something is using the MKIDs as an order sorter for an Echelle spectrograph. So an Echelle spectrograph is a high order diffraction grating commonly used in astronomy for high resolution spectroscopy. You take light, you bounce it off this high order Echelle, and it disperses the light in one dimension, but it has many different diffraction orders overlapped on top of each other. Then you usually use another grating or a prism to disperse the light in another direction. So you have a bunch of lines, and the XY position maps wavelength into position on the array. And so you can get a high order Echelle spectrograph. The really neat idea with an MKID, though, is that you don't need that cross disperser. The MKID can tell you the energy of every photon. So if you have a sufficient spectral resolution in your MKID, you can keep the light in a long linear order, and then you can tell what order it was in by measuring its energy with the MKID. So this is an example of an array we built for that. It has 2,048 MKIDs in the Y direction and has 5 pixels in the X direction. And so this is an example of something we call an HRMOS, a high resolution multi-object spectrograph. We want to be able to build spectrographs with R of 50,000 or 100,000 that can take 100 fiber inputs at a time and give you read noise free, temporally resolved spectra of all kinds of things. There are some very interesting applications of this for TMT. If you look on this, I will say this is a challenging application for MKIDs. You need quite good spectral resolution to get to high spectral resolution. You can see down on the bottom right here. If you have an MKID resolution of 40 at 400 nanometers, and you have an 8,000 pixel array, you can get to an R of 25,000 spectrograph. If you get to R of 80, though, you're up here at 75,000. So, and this seems doable. We think we can push our MKID resolution here without too much, now that we understand what's going on and have the quantum limited amplifiers, that looks like we're in shooting distance of it. So we're very excited about this method for doing high resolution spectroscopy. Another thing that I'm working on with a professor at UCSB, Sebastian Strykan, is using these arrays for light sheet microscopy, or sometimes called selective plane illumination microscopy or SPIM microscopy. This is the idea here is you use a light sheet microscope. You send a beam of light through a sample, and you scan the beam to make a sheet. And then you look at the light scattered out of the plane, either through fluorescence or scattering. And then you can move that sheet up and down and create a 3D image of the full array. The really neat thing here is that the SCMOS detectors that are currently used for this are they run about a kilohertz frame rate, which is pretty good. But the MKIDs have zero read noise, zero dark current, but they're also like 1,000 times faster than the SCMOS. So we think we can even track things like nerve impulses in real time using the MKIDs. We also have the spectral resolution, which allows us, for instance, to probe multiple fluorophores at the same time, which is something, and maybe many multiple fluorophores. We also can go into the near infrared, which is something that lets us penetrate tissue deeper. So I think there's a lot of really interesting microscopy applications in biology for MKIDs, something that I'm looking forward to doing some more on. Another thing we're thinking about is making a light scalar dark matter detector. So this is a concept called an optical haloscope. It uses a dielectric stack to convert dark photons, which are a dark sector force carrier, into normal photons. And they come out in a collimated beam, which we can then focus down onto the MKID array and detect. So this allows us to probe this energy range below 1 electron volt for light dark matter in a way that is very difficult to reach with other technologies. It also can be used if you add in a magnetic field. It can also do axion searches in this energy range. And we proposed an experiment called Deep Dish, and you can see that in this sort of 0.5 to 5 micron wavelength range, or down to 0.2 eV res energies. It's fairly simple for us to set to exceed the current dark matter detection thresholds by 3 or 4 orders of magnitude. So this is something that we are not actively pursuing at the moment, but are looking for an opportunity to make happen in the future. All right, so I talked about a bunch of applications for MKIDs today. I'll say that this is that there are others: satellite reconnaissance, X-ray beamline studies using X-ray versions of the MKID, semiconductor process debugging with X-ray fluorescence spectroscopy, laser communications, quantum key distribution, and other quantum optics applications. Interfacing with large numbers of trapped ion qubits is in situ looks like another interesting option. Biological imaging, and even fundamental physics like the light scalar dark matter project. I'll leave you with a slide that was initiated by my advisor, Jonas Muzinis, that shows the number of pixels in submillimeter detectors over time. The MKIDs share a lot of heritage and technology with these submillimeter detectors. And as we hop to the UV optical, you see our power law has shifted over to the right, but we're still on a sort of exponential growth path where the TESs have sort of leveled off in their pixel count. So I think that the MKIDs are a really great technology, especially when you need pixel counts above around 5,000 or so. The MKIDs really shine as a technology there. All right, so here's my takeaways for the talk. I want you to remember that we've built superconducting optical and near-infrared detector arrays that can count individual photons and determine their energy without filters or gratings. On a pixel-for-pixel basis, these are the most powerful UV optical and infrared detectors in the world. We're aiming to use these detectors to revolutionize astronomy by taking low-resolution spectra of everything, starting with extrasolar planets, and there are exciting applications outside of astronomy. Thank you.
Great talk, Professor Mazin. Thank you. So now we are open for questions. If there are questions, please unmute yourself and go ahead.
Can I ask a question?
Yes, please.
Hi, this is a spectacular talk. So one thing I wanted to ask, you showed that based on the intensity, you can determine the frequency. Does that mean that now you don't need filters to do spectroscopy? Can you just do with their signal itself?
Yes. So let me put up this picture again here. So we can do it. It's low resolution spectroscopy, right? So, or medium, you might call it. So each, if we illuminate with a 406 nanometer laser, that's this spike right here, right? We can easily tell the difference between this and a photon that's, at whatever. So we can absolutely do spectroscopy. I even have an example of it. Here's a, let's see, it's my backup slides, I think. Yeah, so this is a spectra of an object that the red was taken with the Caris instrument and the blue points were taken with the MKIDs. So yes, we can do spectroscopy with these detectors just in the bare detector itself. And by combining it with these things like these in these linear strips and with the shell gratings, we can even do high resolution spectroscopy.
I see. So in the actual telescopes, there is no filter that is put when spectra are taken.
Right. Yeah. So if you want to think about it, you're replacing if you have an R of 30, you're replacing about 30 sequential filter measurements with one exposure. So it's 30 times more efficient if you're looking to get a low resolution spectra of an object through filters.
I see. Thank you.
Professor Roja?
Yeah, thanks for excellent talk. So, Benjamin, I have two queries. So first is about MKIDs. So it's fantastic to see the simultaneous coverage from UV to maybe mid-infrared, I think beyond 5 micron. But my question is that how is the throughput, or maybe in terms of energy resolution, particularly beyond 2 micron, these will be very useful because there is a notorious thermal background beyond 2 micron. So if you want to use for simultaneous, what do you suggest in astronomy?
Yeah, so we currently limit our detectors to about 1.5 microns with filters that block between 1.5 and 400 microns like a brick wall. Because as you said, the thermal blackbody radiation from room temperature kicks up. It's honestly by 1.6 microns, there's a lot of counts. So the MKIDs have limited count rate, right? If you have too many counts hitting a single pixel, you'll see that, you'll get another pulse riding on the back of the first pulse, and that's going to lower your spectral resolution. So what we do is we limit the detectors to like 5,000 counts per pixel per second or so, which turns out not to be much of a constraint in astronomy because we tend to be looking at faint things anyway. Yeah, as you push into the near infrared, this becomes more and more of a problem. So the ways to fix it are, one, you can use a high resolution spectrograph like I showed before. So if you disperse the light over many pixels, that can help deal with the thermal blackbody background. You can go into space and have a cold space telescope, so you don't get those photons in the first place. But it is, that background is kind of irreducible if you have a warm telescope. And so we, if you want to push out to those longer wavelengths and look at warm room temperature things, you're gonna have limits on that.
Okay. Okay, thanks. Second quick query is about, so do you mean that you plan to have a coronagraph for the late type star like M type? I guess most of these were done with Subaru on hot stars. So that is what you were mentioning, or I missed out something?
No, so the Subaru Skexeo instrument, shown here, has several different coronagraphs in it, and the data that we're showing here is taken with a coronagraph. So there's a star in the center here, but its light is being suppressed by this coronagraph in the center. So we are using coronagraphs at the moment, and the ones we're using are broadband, but there are certain coronagraphs that are optimized for certain wavelength bands. And so for the M stars, we'll be working around a micron is probably the sweet spot for this. And that, we have chronographs that will be developed specifically for that wavelength to give the best possible performance.
Thank you very much.
Alok Ray?
Yeah, very nice talk. I have two questions. Number one, you mentioned satellite-based reconnaissance, but for astronomy, what kind of advantages would you have if you were to put these detectors in space platforms? And number two, do you have capability for polarization information? And number three is again, can you extend these capabilities to even beyond longer wavelength of millimeter waves?
Okay, I'll take the easy ones first. We don't have built-in polarization capability. We could probably add it by changing the geometry of our inductor to be more polarization sensitive, but in the optical and near infrared, it usually turns out to be easier to build a polarimeter and stick it in front of your array than to build it into the pixels. So it's something that we've thought about, but we haven't implemented it. There are millimeter and sub-millimeter MKIDs. There's an active community developing them at JPL, at Berkeley, for the CMB experiment. So there is a large, and a NIST especially. So yes, there are a lot of the detectors look a little different because the absorption, you usually use an antenna to absorb the photons instead of just absorbing them directly in the metal, but they definitely exist. The third question was about the satellite. Oh, well, let's just say space platforms. I don't know too much about looking down, so I'm going to talk about looking up. So in space, the MKIDs are really like most of our work is actually funded by NASA because they're an amazing technology, right? They should be extremely radiation hard. They don't have false counts, and they have amazing cosmic ray rejection. Because if a cosmic ray hits anywhere in the array, the whole array lights up. So it's really easy to see the cosmic rays, but they only knock you out for a couple hundred microseconds. So you can do really good cosmic ray rejection, and since you have no false counts, you can integrate to very, very faint objects. So I think it depends on the application. I think they're very exciting for space, even in the optical and near infrared. I haven't mentioned the ultraviolet too, where MKIDs have really good spectral resolution in the ultraviolet. You have to worry a little bit about contamination issues in the ultraviolet, but I think but the traditional semiconductor detectors often have trouble because they have to knock an electron out of some dead layer on a CCD or out of a photocathode on a microchannel plate. With an MKID, they're an energy sensor, and they essentially have 100% QE in the ultraviolet. I think they're very interesting UV detectors. I didn't mention at all quantum efficiency today, but the built-in quantum efficiency of the MKIDs is about 35% based on the reflection off these platinum silicide films. We have implemented anti-reflection coatings on top that boost the QE up to 75, 80%, and we're going to keep working on that. And the QE should be very similar to commercial like semiconductor detectors by the time we're done working with the anti-reflection coatings.
Vijay?
Thank you.
Vijay, do you have a question?
Yes. Yeah. Hi. Hi, Ben. Thanks for a nice talk.
Thank you.
I have a more technical question on the MKIDs and the the whole detection chain and everything. What's sort of the next steps? Is it already as good as it can get, or are there still further improvements in connected to the TUPAs, and are there saturation issues, signal to noise ratio issues? Are they working as quiet as they can?
No, they're not. Well, so the quantum, using the quantum limited traveling wave parametric amplifiers, our last paper we got to about 2 times the quantum limit. Mostly because there was the amplifier, the power amp we were using didn't have quite enough gain. We're getting a new power amp that should essentially get us to the quantum limit. That doesn't quite get us to the Fano limit. So there's detector improvements we need to do to keep all the photons in the right place, the photons and phonons in the right places, and eliminate some sources of noise. But I think my estimate is that in the next 3 years, we'll push our spectral resolution from like 32, like we have it now, up to maybe 80 or so in the optical. The other thing we'll do is work with the people who make the traveling wave parametric amplifiers, like Peter Day at JPL and NIST, to try to package those into more usable packages so that we can integrate them more easily into our readout chain. So those are the 2 things that I think are standing in the way of much higher performance. In the meantime, there's also the room temperature readout chain to start thinking about. And when you start having quantum limited noise, the signal to noise ratio of the analog to digital converters in your readout chain starts to get pushed. And so it's, we may have to back off on the number of channels that we read out on a given board based on the SNR of the ADCs. It depends a little bit on what readout power we can push through the detectors and some other technical points, but they all kind of play off each other. But the nice thing is I don't see any real fundamental limits at the moment that are going to stop us dead. And I think we're going to be able to push on to sort of near Fano limited devices in large arrays with reasonable readout chains.
All right, great. Thank you so much.
Shriharsh?
Yeah. Thanks, Ben, for the wonderful talk. This was nice to hear about the progress.
Nice to talk to you again, Shriharsh.
Yeah, nice to see you. So you mentioned that you're limiting the count rate to about 5,000 counts per second per pixel right now, and that obviously depends on the time scale which you put on the MKITs. But for astronomy, of course, we work with low light sources. But for biology, for example, you could increase the light source and have a faster, get better SNR at shorter time scale. So can you talk about the trade-offs that would need to happen, or how we can go to higher count rates?
Yeah, so there's a couple. The easiest one is to increase the number of pixels and just spread your PSF over more pixels. Because the MKIDs don't have noise, there's no read noise, you don't pay as big a penalty as you would in like a normal CMOS detector or something. So that's the easiest one. After that, you have to start playing games with either the pulse itself. So you can change the fall time of these pulses by, say, running the resonator warmer is one way to do it, or by intentionally changing the film you use in a way that hurts quasi-particle lifetime. The problem is that you start losing spectral resolution. So there's a direct trade-off between spectral resolution and maximum count rate. So there's optimizations that could be made there, especially if you are, if you only require R of 10, for instance, you could play some games to up your count rate. So it really depends on the application, and we haven't gone that far down the road of optimizing for high count rates. One of the things in biology, though, is there's bleaching effects where if you turn up the intensity of your source, you can change or destroy the biological sample you're looking at. So it's TBD whether that's going to be a big problem or not for the MKIDs as we start playing around with it. We haven't really gotten off the ground with that yet. We've done some preliminary thinking, but we're still a couple months away from doing actual tests. So hopefully we'll learn the answer to that soon.
Sure. Thank you.
Pratap, you have another question?
Yeah. So I wanted to ask about the materials aspect. So, right, what are the sort of materials of choice for the MKIDs? I saw titanium nitride, PTSI, and then some indium buffer. So what are the directions at the moment?
Yeah, so a good MKID material has a TC that is 8 times higher than the base temperature of your refrigerator. That's where you essentially freeze out all the quasi-particles and get to sort of a quiet base state. So if you're using an ADR, that means you want something with a transition temperature of around 800 millikelvin. You want something that has a moderate, a fairly high surface resistance above the gap, so normal state resistivity of 50 or 100 microohm centimeters. That gives you more kinetic inductance and lets you make a smaller structure. And then you want a quasi-particle lifetime that's reasonable, like 50 or 100 microseconds. Some materials like tungsten silicide have light quasi-particle lifetimes below a microsecond, and those are just too fast for us to really measure. Finally, you want something that makes a good microwave resonator, so high QI, and that's not true of everything. For instance, molybdenum might sound like a good material. It's got a TC of like 800 millikelvin. It's a little low resistivity. It's kind of like aluminum, but that was an obvious one to try. but like no one has ever made a good molybdenum resonator because it turns out it makes a oxide on the surface that's a normal metal and really lossy. So, you know, there are some of these weird chemistry effects that get you. So not everything works. So we've gone through and tested a lot of these things. I actually have a paper up on the archive that goes through every MKID material anyone's ever tested. It was a chapter in a book and like talks about what's been done and the stuff that's not actually published. But you know, when you go through all those different criteria, you come up, you know, the other criteria is you don't want it to be too complicated to make. So we try to stick to elemental or 2 compound superconductors. So we started with platinum silicide. It has a 930 millikelvin temperature TC. It's stoichiometric. We don't have to play games like we did with titanium nitride to get the right TC by starving the films of nitrogen. And then we switched to hafnium because we wanted something simpler and something with a lower TC to work in dilution refrigerators. So we spent a lot of time thinking about these materials. Unfortunately, no one else has. So it's been an interesting process of discovery.
Thank you.
Are there any more questions? If not, let's thank Professor Mazin again for this excellent lecture. And yeah, thank you all for the question, patiently answering all our questions.
All right, thank you everyone for inviting me.
Yeah, so we also thank you